NASA's Double Asteroid Redirection Test, DART, will be the first ever mission to test a way to protect Earth from an asteroid strike. But to ensure DART hits its harmless test target, scientists and engineers at APL developed a guidance system unlike anything used on spacecraft before, a system that can direct a spacecraft entirely on its own without any human intervention. SmartNav is a set of computational algorithms on DART that, with the rest of the spacecraft's guidance and navigation system, will independently find the moonlet asteroid Dimorphos and guide the spacecraft into it. Scientists knew from the outset of DART's development that the mission would need an autonomous component, but it had to be very different, something that was free to self-inform and make decisions on its own. As the DART mission approaches its rendezvous with space impact destiny, NASA conducted a press briefing to highlight the advanced technologies involved in the groundbreaking mission. Here are some highlights.
This inaugural planetary defense test mission marks a major moment in human history. For the first time ever, we will measurably change the orbit of a celestial body in the universe. Doing so has clear benefits in ensuring humanity's ability to deflect a potential threatening asteroid in the future. It also speaks volumes to how far our space program has come in just the last 60 years.
Nancy Rode, our coordination lead here at the Johns Hopkins Applied Physics Lab. I guess I was told to say a few words just about how will we know this worked. So I'll kind of pick it up from there, and we can take questions. But one of the first things we'll know is that these Draco images that Michelle was talking about with SmartNav are going to be coming back to Earth at 1 per second in real time during the actual impact event. They're going to be really exciting. It's going to start off as a little point of light, and then eventually it's going to zoom and fill the whole entire field of view of the images that return. You'll be able to see things at tens of centimeters per pixel, and these images will continue until they don't. So that'll be a pretty definitive look into the final moments of the DART spacecraft. But LichCube that we heard about that deployed successfully will make its close pass 3 minutes later, and it's equipped with 2 cameras that are going to capture direct images of DART's collision and then the ejecta, the pulverized rock that's thrown off during this collision. But LichCube stores its data, so we won't get those in real time on the actual time of the event. They'll come back in the days and weeks and months that follow after there. We'll also have some telescopes around the world and in space that will be looking at the collision both before and after, and they might immediately see some brightening because of this ejecta, and that'll also be a good indication that this whole collision happened. But none of these things that I've mentioned are actually going to tell us how much we deflected the asteroid. You have to use the telescopes here on Earth in order to make that measurement. So telescopes here on Earth discovered this Dimorphos asteroid system back in 1996. They've been studying it for decades. Very precisely, we know that right now it takes 11 hours and 55 minutes to go around. DART's collision is expected to change that just slightly, a bump, like Dr. Zabukin described it as, only about a 1% change, but maybe 11 hours and 45 minutes going forward. And these telescopes will need to take data for the weeks after DART's collision in order to make that measurement very precisely and figure out how effective was this deflection. And I'll just add, it doesn't really, combined with the telescopes, it really is an international issue for planetary defense. We actually have telescopes on all 7 continents that are involved in the DART observation campaign, as well as telescopes in space that are involved. So we're really bringing all resources to bear on this problem. I mean, the Draco images, the plan is, and maybe I'll let Michelle jump in here a little bit about SmartNav, but these images come back to Earth at 1 per second, and the plan is to broadcast them live on the NASA TV broadcast. And like I said, these will be pretty stunning. Michelle, do you want to give us a description of what this is going to look like for the last hour of the mission?
Well, for the last hour, starting out of an hour, it might be hard to see the actual asteroid that we're looking to hit, Dimorphos. And then really it will start filling the field of view of Draco camera at about 2 minutes out and closer. So we're, like Nancy said, we've seen it, so we are honestly super excited to see what it's going to look like. And I think related to SmartNav, one of the things that we've been able to do with SmartNav is we've been simulating what the asteroids could look like and different shapes, using existing asteroids that we've already seen and using that to test our robustness to finding Dimorphos and hitting Dimorphos.
Last 4 hours, we go into something called the terminal phase of the mission. So this is we're going for Dimorphos, and we're going to do everything we can to make sure that Draco stays pointed at Dimorphos and Dimorphos, the system, and that we're heading in there. So at that point, we are doing no more planned ground commands, and it is all autonomous onboard spacecraft control. So SmartNav's taking the wheel and steering us in. At that point, at 4 hours, we are actually targeting Dimorphos because we can't see Dimorphos. And we're going to continue to target Dimorphos all the way until about 50 minutes to impact. At 50 minutes to impact, we will have been seeing Dimorphos for maybe 40 minutes, something like that, and we will transition our 1/4 degree field of view slightly over. So actually both objects will still be in the field of view, but we're going to go straight toward Dimorphos and go for impact on there. So that's at 50 minutes to impact. That's a very sweaty time for us. So we have a lot of contingencies built right around that 50-minute transition. We're going to be watching the telemetry like hawks, very scared, but excited. And then from there, at 20 minutes to impact, we're going to something called precision lock, which we totally ignore Dimorphos, and we just go for Dimorphos only. We expect to be thrusting quite a bit at that period. At 2.5 minutes to impact, we cut off all thrusting, and we're going to coast in. We're going to be streaming images the whole time. So images are coming in through Draco, through our avionics, and right off the radio. We expect the data to only be on board for less than 2 seconds, and then the DSN will receive it. We'll get it on the ground.
If you look at landing on Mars, if you land on Mars, frankly, it lands whether you watch or not. And assume everything goes well, you can get the data back the next day if you missed a pass. That's not the case here. There's nothing to watch. Assuming everything goes well, a few seconds after the impact, there's nothing to watch. So I just really want to make sure that everybody understands how important it is that for the whole ecosystem to really focus on that, especially in this case, the Deep Space Network system, which of course is over the time is including everybody, all the stations around the Earth, the 3 stations. So that's number one. The question you also asked is what will we see about the impact, and frankly, I think where you should err right now is basically assume you will not see the impact other than through the amazing footage that was just described right now, from the camera itself. But wait, and for us, I think the principle we have here, and I think you described it really well, we gave ourselves many chances to get lucky, looking from many different directions. We just have to see. I mean, just everybody should expect that we're trying, but if I was in a live broadcast, I would not promise that, just because I don't think that's a requirement at all. We're just going to try, and frankly, we're turning every head we can, from James Webb Space Telescope to ground-based systems and so forth. So to try to capture a glimpse of the whole process here.
There's JWST, Hubble, and also the Lucy spacecraft are going to be operating in space.
Dimorphos is 1 kilometer across. That's pretty small. Dimorphos, 120 meters, 160 meters, somewhere in there. We can't see it until an hour and a half before we get there. So we're flying in something that it takes 38 seconds for us just to communicate one way with this thing. More than a minute to get the full round-trip light time to get a command there and back. But yeah, there's just an incredible amount of technical hurdles here, keeping all the systems online, up and running. You're taking these images, you're bringing them down to the ground in one stream, and another stream, you're dissecting them on board with an FPGA that's never been flown in space before. So you're running these blobbing and centroiding algorithms and running them through these filters that have only been used on missile defense. So this is an incredibly challenging problem that we're very excited to tackle and very hopeful.
We have done so many simulations and again, varying the shapes and the conditions and spacecraft fuel, everything. And so we are optimistically confident that we're going to hit Dimorphos, and if we see it, we should hit it.
The amount of ejecta, if you wanted to ballpark it, of course we don't know specifically, which is why we're doing this test, but it's something like 1 million kilograms. Now, 1 million kilograms sounds like a lot, but we don't know the mass specifically of Dimorphos either, but it's something like 5 billion kilograms. And the mass of the spacecraft, to put this all into perspective, is 600 kilograms. Okay, so the spacecraft is very small. Sometimes we describe it as running a golf cart into a Great Pyramid or something like that for Dimorphos. This really is about asteroid deflection, not disruption. This isn't going to blow up the asteroid. It isn't going to put it into lots of pieces. And in fact, the way that we're shifting Dimorphos is going to orbit ever so slightly, even closer, more gravitationally bound to Didymos than it was prior to DART's collision little nudge that only changes its orbital period by 1%. So it's going to be pretty spectacular for sure, but in the grand scheme of things, it doesn't make any noticeable change in how Didymos goes around the Earth or a threat to the Earth in any way.
There is no scenario in which one or the other body can become a threat to the Earth. Literally, it's just not scientifically possible with just because of momentum conservation and other things.
Yeah, this is Nancy Chabot. So the Didymos asteroid system was discovered in 1996, and people have studied it extensively since then. We know the spectral composition of the larger Medford Didymos, and it's an S-type asteroid. It's the most common type of asteroid in the near-Earth object space. It's like ordinary chondrite meteorites. We have samples of these. We study them in the lab. They're mixtures of metal and rock at an intimate mixture of early building blocks of the solar system, which is very exciting and not the topic of today's conversation. Dimorphos we haven't seen, but the models for how binary asteroids form suggest that it's likely going to be the same material as Didymos. And so we have good reason to believe that. It is exciting that Dimorphos is going to be the smallest asteroid that's ever been visited by a spacecraft. So what is the structure of these small asteroids? Are they rubble piles like these other ones that we've seen? Most scientists would probably bet on the rubble pile rather than the coherent shard. And that's one possibility. But again, I think to put this all into context, the DART spacecraft is very small still compared to Dimorphos, and this is just a small nudge. This is what you would want to do for planetary defense. You're trying to just give something a small nudge which only changes its position slightly, and that adds up to a big change in position over time. So if you were going to do this for planetary defense, you would do it 5, 10, 15, 20 years in advance in order for this technique to work. You're not trying to make yourself a problem where you destroy an asteroid and you make a lot of different pieces, and so this really is there. So we don't, to say we don't know anything about the asteroid system, I think is not right. We actually know a lot about this asteroid system. We've been studying it for decades. We know the composition of the primary, but there's going to be a lot to learn here.
So we're not aware of a single object right now within the, next 100 years or so is really threatening the Earth. I'll also guarantee to you that if you wait long enough, there will be an object. Work from OSIRIS-REx, for example, as well as other small body type of missions have also added to the forecasting accuracy of such threatening asteroids. For example, the interaction of thermal radiation and the orbit that is actually really hard to predict based on theoretical context. For OSIRIS-REx was specifically measured and being put in context with the observations of that body, which really helps us, together with the mass distribution in the asteroid belt, which we get to know better and better to really knock down, if you want, the biggest uncertainties for orbit propagation over long periods. So the point is, yes, this impact is what we want to do with the NEO Surveyor, really looking at all threats, but also really understanding the science behind it that really helps us with a more accurate kind of long-term predictions as we go forward.
In addition to the rows of solar arrays, which you guys are quite familiar with, they dwarf the spacecraft itself. We also have a radial line slot array, which is the high-gain antenna. This is a novel design for a high-gain antenna that basically uses a leaky wave antenna design so that where energy leaks out of the circularly polarized to form a beam slot. So we're taking technology that's being demonstrated on DART, and we're actually going to use that on our Dragonfly mission. So this is an example of where That technology is being tested out, and we'll actually implement it on future mission. We also have NASA's evolutionary Xeon thruster, or the Next-C thruster. This is a solar electric propulsion system that basically accelerates Xeon. This is, once again, a demonstration mission. We've demonstrated its ability to operate correctly early on in the DART mission. And then we also have the transformational solar array. These is a small batch of IMM4 solar arrays and reflectors that are actually embedded into the ROSA solar arrays. These produce 5 times the power and packing density, and once again are used, ideally would be used on outer planet exploration missions with large solar arrays. And so these are very exciting technologies that we're hoping that we are learning a lot about, and hope to implement them into future missions. So,
if DART collides with Dimorphos and then you don't see any orbital period change, this would be exceptionally surprising, because even if there's no ejecta, just the amount of momentum that DART is bringing in on its own from the weight of the spacecraft slamming into Dimorphos is enough to shift its orbit in a measurable way, because the telescopes are very good at making this measurement. How much we shift it is really what the measurement that we're looking to make, and that's related to how much ejecta comes off, how the asteroid, this real asteroid, interacts with the DART spacecraft.